Okay, under class notes, I have a excerpt from a chapter on different things that you'll see in 2D orthographic drawings and how they're represented. First off, and I think this is mentioned in one of the Solid Professor videos, fillets and rounds. Okay, a fillet and a round. Let me see if I can zoom in on that a bit. There we go. They're rounded surfaces. Okay. A fillet is an internal round, and a round is an external round. So here you have round, and usually what this means is that the surface, that the material isn't finished. Usually, it means it's not finished. It's like a cast metal. Okay, and then you'll get sharp right angle edges for surfaces that have been finished, grinded down, and sharpened edges and things like that. So, let's see. Different examples here, like how certain cast pieces might be represented. We have the fillet come in and fill it up here, if like that was the piece there. Likewise here, it's very similar. Actually, okay, here we have the part come all the way to the corner where this comes up, juts onto it. Might go inwards depending on how it looks. Okay, it depends on the part. Best judgment as to what's going to look best. All right, so like for example, in like this part here, say we got unfinished cast parts here. You can see the fillets, and then the edges, the outside edges, you can tell that they were cut or machined because they got nice sharp edges. So down here, this is finished on the bottom and on the back, but then the rest of it's cast. Okay. All right, yeah, runouts are when you hit a point of tangency. So, like if you have something like this, it's going to come up to that corner, and then you'll have a little curve up. And the only way to really do this in the CAD is just to draw a little arc there. It falls at the point of tangency. Now, if this were a finished piece, there would be no run out. It would just be a straight line, and it would end. All right. Edges. We talk about edges in, showing the edges with your object lines. Sometimes it's not real clear cut. Like, say you have like an I-beam here or something like that matter. It's conventional practice to show a line, to show where it is, where the major bend is, even though in true projection there would be no line because there's no sharp corners. Okay, but in something like an I-beam like that, you can show, a couple little lines just to show where those bends are. It can often be a judgment call, but if it's something really obvious, like here's some examples of things that the true projection view just doesn't give you any information at all. Okay, whereas these ones, where they add some lines in here to kind of show what's going on, even though there's no sharp corners here, it's all rounded edges. It helps to show, what's happening there. It's more descriptive. So whenever, like they say, don't break any rules unless it helps the drawing be communicated better. This is like the classic example of that. These aren't true projections, but they do show what's going on a heck of a lot better than any true projection does. All right, let's see. Views, necessary views. How many views do you need for an object? Well, okay, like this right here, this is an example of a typical one-view drawing. All right, you don't really need the side view here. Just like a note that says how thick it is. And we've encountered that with some of the drawings we've done. Well, have we? No, I'm thinking of the other class. Where there'd be a plate and it just says like, 1/8 inch thick or whatever, or, 8 millimeters thick, whatever it is. So in this situation, there's nothing really that you're going to get out of a side or a top view. So that's fine. Right here, you do need the second view to show what's going on here with this shape. Okay, a right side view would be kind of unnecessary. You wouldn't. There's no information you would get out of the right side view that you're not getting out of here. The right side view, you would get the width here, or the height of the object. Okay, you would get the thickness here, and this thickness up here, and all that stuff is found in these two drawings, these two views. So you don't need the right side view. All right, move, cat. You are annoying. Kitty. Okay, anyway. Stay on my stuff. All right. And then here's an example of a 3-view drawing. And where all 3 views are necessary. If you just 2 of these views don't come back, like, if we just did these 2 views, we have no idea what's going on up here. We have no idea how to find the location of these holes. If we had just these 2 views, we'd have no idea what's going on right here. If we had these 2 views, which would be really weird, we would have no real indication as to this shape. So, yeah, here's just some different examples of where they show this view is unnecessary. But if it's symmetrical, chances are you can get 2 views. Okay, so these are symmetrical objects, cylindrical objects. This third view right here, this top view, is exactly the same as this view, so it's completely redundant. This view here doesn't show us anything we can't get in these 2 views. Okay, any information that we would get out of here can also be found up here and there. All right, partial views. Okay, one thing about, now we've talked about 3 views of top, front, and a right side view. Okay, that's pretty much the convention, but not always. It's not 100% that way. Anything, in any way we can do less work and still efficiently convey the information is good. So, for example, here's a part here. All right, and instead of having a front, a top, and a right side view, they're doing partial views of the left side and the bottom. Okay, a right side view, true projection, would show you nothing that you couldn't get from this. A top view would give you nothing that you couldn't get from this. Okay, so instead of drawing all this stuff out down here, and just break it. Draw the relevant part that you want to look at, and then there's a freehand small break line in here. The break lines are thick like the visible line or the object line. And, well, it depends on what kind. A short break line, and it's just kind of a freehand squiggle. Okay, situation like this, with symmetry and usually with things like these cylindrical or rounded parts, it's like a flange or a piping cap or something like that. This other side here would be completely identical to this side, so you can do just a broken view or a half view. So you got the front view, and instead of drawing the whole circle, you just draw half of it. Or in this case, you can also do it this way. You just do if you want to show that rib a little bit clearer, you can just do a short break right here. If you're doing it straight down the center line, though, you don't have to do the squiggly break lines. You just put that center line in there. And it's about efficiency. It's about saving time, really. Because, especially back in the day when everyone was drawing by pencil and paper, saving as much time as possible to pump these drawings out so you can get everything into production was critical. So what made AutoCAD so huge is because we cut drawing times. drastically. And you still get the information out. There's less to read. There's less stuff on the paper. There's, open up some room for other things. Okay, here's another type of partial view. And this is a situation where you have, here's the front view of the object. The right side view, notice we're just showing this face right here. Okay, the back here would just confuse things, which would look like this. It would add a bunch of hidden lines all over the place. So if you can eliminate hidden lines like that, that's okay. So here, this is all identical. And then we have a side view here showing, just what you would see on his face and nothing behind that. And likewise on the left side showing this stuff with nothing behind it. Because these two sides are different. A top view isn't going to give you anything. Top view is going to give you, maybe the thickness of this stuff that you can get down here. So eliminating this stuff from the left side view eliminates a lot of hidden lines, which can cause confusion. Same thing with this side here. Okay, details. We got a question. Or is that someone popping in? Is that someone popping in? Where was I? Okay. Details. If you want to zoom in on something in a drawing, so you got a complex drawing, you have the phantom lines with a circle and arrows that cut around it, and then you would cut that section out in a separate detail on a different part of the drawing, like say on this side of the sheet, and this detail. And then you would denote your scale too, because you're probably gonna maybe make it larger so it's easier to read. Breaks, conventional breaks. Okay, different ways of doing breaks. If you've got a cylindrical part like a solid round bar, okay, you can have kind of an S shape, and then the hatching for the solid part. This is the same thing, except for it's a tubular thing. It's a like a pipe, and with a pipe you would show the interior diameter, okay, right here, and then just section the parts that would be considered solid. Again, here's a break in a section view of a pipe of some sort. Different types of breaks. Yeah, this right here with the wood. I mean, just a basic short break would do as well. And here's a typical use for a break. Like, for example, and this has probably been said before. Let's say you got this rake here. It's 6'2", okay, and you've got a drawing space. Well, of course, you're obviously going to scale it down. But let's say you got 12 inches of object and you want to put it on an 8-inch sheet of paper. You can't put 12 inches on an 8 because it's going to be too big. So if it's a lot of the same thing, break it, and then put the dimension on it so you know what's going on. Okay, our alignment views. Again, we went with usually go with the front, the side, and the top view, right? Now, as this says here, 3 views in correct alignment, but poor choice of front view. It is a bad choice of front view. I would make this my front view right here, and then I would have the top view, which would look a lot like this, and then the side view, which would look like this rotated. It would just looks better. Here we go. This is exactly what I was saying. Okay, it's not the same object, but something similar. Where is it? That is the same object. Oh, they flipped that. They flipped that right there, which is, yeah, I see it. Okay, so. Yeah, and it's got to line up. See this right here? This is like, I've gotten stuff like this. Don't do this, please. Everything has to line up. It's got to line up. That's the whole point. It's orthographic projection. It's a projected view. So everything has to line up. You don't just randomly place views out there and assume that people are going to understand what it is. Right? and make sure the views are proper views. And you don't want to put the right side view on the left of the object or what have you. All right, back out of that. Remove views. A removed view is like, remember we talked about the detail here, okay? There's the detail. When you do a detail and you do a little circle around something to show a detail and zoom in on something, and then you're going to show it somewhere else on a drawing. A removed view is sort of like that. Okay, here's a situation where, yeah, they have a front, a top, and a left side view. All right, and there's a reason for the left side view, which I'll get to momentarily. Hold on. Okay. So there's a reason for the left side view we'll get to momentarily. If you look, we have the front, the top, and the left side view. And the left side view, we can't see the what's going on back here. All we have is some hidden lines. And hidden lines, one of the general hard rules of thumb is you avoid dimensioning to hidden lines. So you want a good clear view of that. So the only two ways to do that would be to cut it and make a section view, or do what's called a remove view. And you have a little viewing plane line, which is identical to a cutting plane line, but the difference between a viewing plane line and a cutting plane line is a cutting plane line goes through the object all the way through and cuts it, where this doesn't. This just pops in here, so it's like your little guy standing here and you're looking at it from this without this in your way, and then you can just draw the partial view of what's happening right there, so you understand that. Now the reason for the left side view instead of a right side view, well, a couple. A right side view of this orientation right here would give us the back end of this part. We would be looking at this. So all we would see is the back end of this. This circle would be hidden line. Okay. This little cut would be a hidden line. And then all of this stuff, all of the boss down here would be hidden lines. So you would get the back end view of that, and it would be really messy with a bunch of hidden lines. Okay, well, you say, why don't we flip it? Why don't we put it so the back here is over here, and this is over here, so we have a right side view that looks like this. Okay, the only reason why they don't flip it, remember I talked about how important it is to try to avoid hidden lines if possible, is because if you did flip it, then you would not have a clear view of this little cut right here. Okay, and that would end up being hidden, and you want to at least try to get one good clear view of every surface, every edge if possible. So because of this one little notch right here, you're forced to present it like this, and you end up with a left-hand view, which is fine. I want to talk about that right there. Okay. Revolution conventions. I used to make jokes about revolution conventions being where a bunch of guys in funny uniforms go to Vegas and get drunk and yell "Viva Afghanistan," but then politically that's charged these days, so I avoid that joke now. There were simpler times once. Revolutions, get a revolution, get all these revolutions in South America and whatever. Anyway, revolution conventions. So in a situation like this, we've got this flange here, and we have these ribs. In true projection, you get this. Okay? And this becomes very, very confusing. So in engineering graphics, one thing that we do is we're going to bend the laws of physics, and we're going to move this part down so it looks as if it were flat, as it looks as if it were coming straight down. Now, we have the information right here where it actually is. This just makes it easier to put dimensions on it and show, the shape of that construct. Whereas this is just confusing. It's kind of a waste of time to draw it because you're not going to get anything out of it. Likewise, over here, we have this part with all these holes, right? Equally spaced holes, there's 12 of them. A true projection would have hidden lines over hidden lines over hidden lines over hidden lines over hidden lines. So to clean that up, it's okay to just put the hidden lines showing the top hole, the center hole, and the bottom hole. And then we can look at the front view and we can see where all those holes are placed. Evolution. So here, another example. This would be the true side view, but we're going to kind of fold that down. We're bending time and space here, folding this down so we can present it like this on the side view, and it gives us a better idea of what these angles are and things like that. And knowing the front view is going to be true, we know what's going on. Okay, holes. So, some lingo here. Diameter. We got a hole here. This says this is the diameter of the hole, okay? And it is a diameter of 19 millimeters, and the depth is 29 millimeters. This capital T with the arrowhead on the bottom of it means depth. So when you see that, it means you're going to come down 29 millimeters for the hole. Okay. Here we have diameter, 22.17. This is a tolerance. Okay. So what they basically do is they round it when you draw it, but that's the tolerance of the depth. So it's 22.17 to 22.23. You can't see the decimal, but it's in there. All right. And there's no depth because it goes all the way through. All right. Counterbores. Okay, here we have the diameter, drill diameter is 0.9. That's this diameter right here. That's the hole that goes all the way through. Counterbore symbol. It looks like a little box, open box. Okay, the diameter of the counterbore, 29. That's this outer diameter right here. Counterbore diameter. Depth is 14. So here's our depth. Counterbore depth is right here. So that's how you read that. The diameter, the main diameter, is the diameter of the hole that goes all the way through, or the drill. And then the counterbore, which is going to be drilled on top of that diameter, 29, and how deep you go. All right, what else we got here? Countersinks. Countersinks are kind of like counterbores, except for they're conical. Okay, you got that angular deal going instead of a square, right? And you've seen the conical shaped like machine screw heads and things like that. So the top view looks just like a counterbore. It could be identical. It's the front view here that we see what's going on here, and the syntax, the designations are: we have the diameter of 14, right? That's the diameter of the drill, just like in the counterbore. Okay, and then we have the counterbore symbol, which is a V. The counterbore diameter is 29. That's this diameter here. The distance from here to here. And then we have the countersink angle, which is, it says 82 degrees. So this angle here is going to be 82 degrees. But to make life easier, more often than not, you just draw it at 90 degrees and then just put the angle in there in your dimensions right here. Or you can draw it at 82 degrees if you wish. It doesn't really matter. but you can draw it at 90 too, just to simplify your life. There's a spot face. Spot faces are really similar to counterbores, but basically a spot face doesn't have a depth because it's just a zit. Okay, they just put the grinder on it or the drill on it just to flatten it out. Excuse me, and they can either be indented or they can poke out. Okay, they have if you, well, I don't know about car engines today, but if you pop the hood on an old 1973 Chevy, you look at the engine block and you see it's all cast, but then there's like little spots, little bumps that have a flat grinded surface on it with a bolt on it. That's a spot face. Okay, it just makes, if you have a cast material and you want to put a bolt and a washer on top of it and have it nice and sit flat and flush, put a spot face on it. And sometimes they go in, sometimes they pop out. It just depends on the situation. And this is just showing how not to draw the things. Like if you were doing hidden lines for this counterbore, the line would come across. Same thing with here because there's edges in there. All right. Anything else in here we want to look at? Now you can see, like right here, we have these two. Here's a countersink and here's a counterbore. The top views are virtually identical. That's why you need that front view to show you what exactly is going on. Jeez. The cat walks across the keyboard. I was talking, and yeah, it hits buttons and keys. And I got up. I was chatting with a buddy of mine on Messenger the other day, and I got up to go to the kitchen because the cat usually sits right here by the laptop. And I got up to go get refill my my tea. I come back and the cat's sitting on the keyboard. So after I propelled across the room, my buddy I was chatting with was like, "What?" And I looked and there was just like all this nonsense typed in. Anyway, all right. So anyway, let's take a look at the assignment. And I'm not going to. I'm just gonna let you guys dig into this one, and I'll go over them on. I'll go over one on. There's two of them. I'll go over one on Wednesday, and then I'll do one on Monday. But go ahead and start them. These are metric drawings, A-size sheet. Okay, here we've got they're cast. Part of it's cast and part of it's finished. All right. We have a spot face and all that kind of fun stuff going on. Let me look back here. Let me go back to where was I? Let me go back to this. We talk about finished parts. Does it have finish marks in here? I don't. All right, well, I'll talk about finish marks when we do it. Finish marks are away. Here's one. This is a finish mark. So when you have a part that's part cast and part finished, excuse me, I put this little V or a little check mark to show that this is finished, this surface. Finish marks, there's all different kinds of finish marks because just a generic finish mark like this is fine if it's just finished, you're just going to grind it. But there may be a texture that you're going for. If there's a certain texture or a different way that it's finished or polished or what have you, and there's ways of adding notes into these finish marks to let you know what kind of finish is required. All right, so that's the first one. And the other one here, again, we have a partially cast object, and we have a situation like this right here. where a true representation, because there's no hard edges or corners on this right here. A true representation would look like this, but that doesn't really tell us what's going on, so we have to come in and play around with this stuff. For the top view, of course, there's hard corners on the bottom view, which we can put in with, we'll show that with hidden lines on whatever view that happens to be. Another thing is they do this on purpose to mess with your head. They put this facing this way, right? Probably really just to show you what the back dimensions are. But a lot of times students will grab it and immediately draw it like this as a front view pointing to the left, and that ends up with a right side view that's got nothing but hidden lines. So flip the object and have it pointing to the right, and then you can have a good right side view and the top view. And I don't recall, but we might need to do a remove view on this one. If, let's see, this is 25 millimeters to here, and that's 30 millimeters to there. Yeah, we're gonna have to do a remove view on this one, because this gets in the way of this, and from that right side view you don't get a clear shot of what's going on right here. Okay, and that becomes problematic. Yeah. All right, a couple more videos in here under standard drafting concepts. I'll probably throw some more up. These videos are like from like 1950 something, but the information is very good. See, it's got like Bobby, and he's going on a date, and he's got a pimple, and he'll know what to do. Anyway, they are very informative, and they just go over the basic concepts between, how to visualize these objects.
Now that you know how mechanical drawing is used,
so if you're having problems, visualizing how this object is gonna fit on a two-dimensional, with the using orthographic projection, these might be helpful to watch. And yeah, they're old, but it ain't changed. It hasn't changed. Science is science. Well, engineering, whatever. All right, guys. Any questions?